Hello, and welcome to today's webinar, GNSS Interference, Sources, Effects, Detection, and Mitigation Techniques, brought to you by GPS World Magazine and our sponsor of the event, Talisman. Talisman is a developer, manufacturer, and provider of GNSS, Iridium, and Global Star antennas and accessories in support of customers who are engaged in a broad range of satellite-based positioning, navigation, and data applications. Based in Ottawa, Canada, Talisman is focused on high-functioning, high-performance technology and solutions. Its core competencies include digital, wireless networks, RF and global navigation, satellite systems, component design. I'm Mackenzie Schoner from North Coast Media, content marketing producer for GPS World, and I will be the moderator for today's event. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please note the Q&A panel at the left-hand side of your console. If you have a question, type it into the panel's text box, then click Submit to place your question in queue. We encourage you to ask questions and enter anything you may have for our speaker during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration for today's webinar have already gone to our panelists and may be covered during the presentation. If you experience any difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and Assistant Producer Grace Ryback or I will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the upper left-hand side of your console. If you are logged into your social media accounts, you can share this webinar's title, description, and URL with your friends or colleagues using the Share This widget in the bottom left corner of your screen. Now I'd like to introduce today's presenters. We will be hearing from Peter Iannucci, Postdoctoral Research Fellow for the Radionavigation Laboratory at the University of Texas at Austin. Peter's current research interests include collaborative navigation, multispectral mapping, and repurposing broadband internet satellites for radio navigation. We will also be hearing from Wim de Wilde, Systems Engineer for Septentrio. In 2002, Wim began at Septentrio, where he created many digital IP blocks and RF front ends for GNSS and in-mesh asset reception. His research interests include anti-jamming and anti-spoofing techniques, multipath mitigation, and sensor fusion. We will also be hearing from Julien Hautcoeur, Director of GNSS Product R&D for Talisman Wireless Incorporated. Julien joined Talisman in Ottawa, Canada as an antenna and RF engineer and is now the Director of GNSS Product R&D. At this time, I'll pass the presentation over to Peter Iannucci, Postdoctoral Research Fellow for the Radionavigation Lab at the University of Texas at Austin. Peter, take it away.
Thank you for that kind introduction. So, I'm a postdoctoral research fellow with Professor Todd Humphreys. I've been, as we say, asked to provide an introduction to the topic of GNSS interference. We can think of GNSS equipment as an elaborate filter standing between the environment and your sensitive user equipment. Its purpose is to extract positioning, navigation, and timing information from the signals in the environment while excluding any other effects from affecting the solutions it provides to the user equipment. So let's consider this environment first. So there are signals of all types in the environment. Only a few of these signals are useful for positioning, navigation, and timing. Most signals are undesirable, and the desirable signals are extremely faint. Some of these signals are natural, some are man-made. Among the man-made signals, some are intentional, others are not. Among the intentional signals, some are GNSS-like, others are not. Among the ones that are not, some are in-band, some are out-of-band, and so on. Any undesirable signal in the environment is a potential source of GNSS interference. What are the sources of some of these interfering signals? The most basic one comes from the thermal motion of electrons in the antenna and amplifiers of your GNSS equipment. This is very small, but it's still large compared to the faint signals that we're trying to pick up. Other sources of interference include black market jammers, which can be plugged into the 12-volt adapters in cars and trucks. They're specifically intended to interfere with fleet monitoring. But illegal signals are only part of the problem. Even signals outside of the GNSS band can cause interference. We've seen a healthy licensed LTE signal from around 780 megahertz interact with our signal amplifiers to generate harmonics inside our receiver. At first, we thought the problem might be the Texas heat, so Talisman sent an engineer up a ladder with a hot air gun to help us track it down. With their help, we eventually fixed the problem by replacing the antenna with one that had stronger filters. We've also dealt with interference from HDMI and USB 3.0 cables when we were trying to add a CD GNSS receiver to a virtual reality headset. These different types of interference affect GNSS equipment differently depending on whether they are narrowband or broadband. More specifically, there are signals that are narrow or predictable so that GNSS equipment can filter them out. And there are signals that are broad or unpredictable so that we can't filter them out without also losing a portion of our precious GNSS signals, sort of throwing out the baby with the bathwater. We can always distinguish between these types by looking at a spectrogram if we have a spectrum analyzer or a suitable recording device. But at the end of the day, many of the best GNSS interference mitigations that you will encounter are targeted towards specific types of interference. And generically, the types that are most difficult to deal with are the broadband ones, because the more unpredictable a signal is, the more sweeping must be the filter to get rid of it. So what's the potential impact of GNSS interference? If the GNSS equipment fails to filter out undesirable signals, user equipment gets affected. This could lead to economic and communications disruptions or even injuries. Cellular networks and power grids require precise synchronization, and automated vehicles will also require precise positioning. So what does this situation look like from the perspective of your equipment? What do you see when there's a problem? Well, for interference that's not deliberate, generally what you will see is degraded availability and degraded accuracy of solutions. In the case of malicious interference, you can have a much worse situation. You could have targeted outages that appear at critical moments or in critical locations, which is particularly concerning in safety of life applications. You could have false confidence in your navigation and timing solutions, or even false solutions altogether. In the worst case scenario of electronic warfare, you could even have permanent damage to your GNSS equipment. Hopefully, none of you will have to deal with that. So what stands between your equipment and this potentially hazardous environment? The GNSS equipment is the filter. Now, ideally, you could treat this equipment like a black box, where you don't need to know about what's going on inside. And our colleagues at Septentrio and Talisman have put in an enormous amount of effort into making that as true as possible. However, interference is always going to mean that you can't quite treat a GNSS receiver as a black box. Interference limits our ability to build systems out of GNSS equipment with clear barriers of abstraction. The equipment can be decomposed into several components. There's antenna, there's RF filters, amplifiers, and there's digital signal processing, which can contain all manner of intelligence for excluding interfering signals. Each of these components plays a role in filtering out undesired signals, and each offers a particular opportunity for excluding unwanted signals and particular hazards based on potential non-idealities at that point in the chain. So what are these opportunities? The antenna is the only place where information about the angle of arrival of a potentially interfering signal is available. If you have a single element antenna and not a SERPA or something fancier, and if that antenna is not particularly directional, that's it. The signal coming out of that antenna will include whatever it includes, and you won't be able to take advantage of the fact that the spoofer is in a different direction than the satellite to exclude it. So the antenna allows you to provide a directionality line of defense against interfering signals. It's also the first line of defense against out-of-band signals. Regarding antennas, Julien will offer a great deal more detail in his presentation. RF filters present another set of opportunities and challenges. It's possible in textbook theory to design a filter that totally eliminates out-of-band signals. But as a general rule, you pay for how picky your filters are with losses. And again, Julien will have more to say about this. The digital signal processor offers a great deal of room for smarts. You can design adaptive notch filters to deal with narrowband interference and so forth. And again, in the case of wideband interference, it's going to be increasingly difficult to do careful surgery to extract that signal and avoid it without also blanking out part of the desired signal. So where does the Radionavigation Laboratory, and this, on the subject of DSP intelligence, this is one of the great strengths of Septentrio, and Wim will be speaking about this in his presentation. So where does the Radionavigation Laboratory enter into this? We are interested in the fundamental limits of providing reliable positioning, navigation, and timing. That means we have to study each of these components in depth, and we divide our attention according to where we believe we can do the most good at the moment. We're also interested in algorithms for navigation fusion and signal situational awareness. This is a topic that's growing increasingly relevant. We are exploring collaborations to do this both with on-the-ground sensors and from space. And some of the people, even who have joined us today on this webinar, have posed questions like, where can I get information about real-time violations of the band plan? Where can I learn about real-time information of where GNSS interference is going on? And there are retrospective databases where you can look at where there were complaints. The NavCen from the Coast Guard compiles some of these, but there isn't really a public real-time database, to our knowledge, that provides that kind of information. So we're interested in collaborations that could develop such a thing. So these sources of interference are the kinds of gotchas that make system composition challenging, even for specialists. And sort of to illustrate this matter of signal situational awareness, This is a map that was developed by some of my colleagues using recordings from the International Space Station as it flew over various parts of the world. And the colors represent how often there seemed to be some sort of disruption to the signals that the ISS was receiving. And as you can see, when the ISS was passing over, a certain region, because the antenna on the space station is pointed sideways, the location of the actual jammer might be a little bit to the left side of these bright circles. It's exciting that you can obtain this kind of information, especially with public data, or data that will be made public and is protected by various treaties. This is not confidential. And we would love to see this sort of capability made commonplace, made real-time, made continuous. So what else can I tell you? We view the purpose of this webinar as being to equip you to recognize the types of issues that you might encounter, so that you'll know if you have this type of problem, come talk to us academics. Why can't we use XYZ plus ABC? So for instance, I'm told that a very common situation is in maritime applications, you have a mast, and somewhere on that, or an antenna pole, and somewhere on that pole you've got a GNSS receiver and an Inmarsat uplink or an Iridium uplink. And these devices transmit with 1 billion times more power than would be comparable to the signals that are coming in from GNSS. And so that it's an extremely significant challenge to engineer components that are ideal enough to exclude these types of signals. And everybody would like to have an Inmarsat uplink on the same pole, but it may not be the type of system composition that's feasible. So if you have the type of problem that's associated with antennas, come talk to Talisman. They have solutions for you. If you have the types of problems that can be addressed with better receiver technology, come talk to Septentrio. Our colleagues there have great solutions for you. And that concludes my remarks. I'll hand it back to you. No, excuse me. No, I'm handing off to Julien Hautcoeur, who will speak from Talisman about their work on antenna technology. Thank you very much.
Hello, I'm Julien Hautcoeur. I'm the Director of GNSS Product R&D at Talisman Wireless. And thank you, Peter. I will now talk about the GNSS antennas and interference mitigation. So first, a little bit about Talisman. Talisman is a Canadian-based company. We are part of the Calian group. And since the beginning, we design and manufacture precision GNSS antennas. We have a very wide range of antennas using different types of technologies like patches, helical, or dipole antennas. They come in all sorts of size and enclosure depending on the application that customer needs and use. So we are definitely some of the experts of that type of product for the GNSS system. Our mission since the beginning is to reduce the costs of those antennas. Since the last 10-15 years, the cost of precision receivers have been declining, and it makes sense that the cost of the antenna must track. So that was our mission, to provide like high precision antenna with more affordable costs without compromising on the precision. So what is the importance of the GNSS antenna? Like Peter said, the antenna is your first component in the positioning system in your GNSS chain. So if the antenna accepts interferences, produce noise, or shift phase of the signal, there is a limited number of things that the receiver can do in order to recover from the signal degradation. So you have to see the GNSS antenna as your first line of defense in the system. This is why the GNSS antenna design choice installation is very critical and should be done wisely. When we talk about interferences, one key advantage to have from the beginning is knowing the environment where your system will be operating. The received power will depend on the distance between your GNSS antenna and the interference source. So more you know about that, and better it will be. First question you have to ask you is, where is going to be the antenna located? Is it going to be co-located with interference sources, like, for example, on a boat, like Peter said, like you could be close to an iridium antenna. On a car, you can have like Wi-Fi antenna, LTE, cell phone, SDR. On drones, same things. Also, where are you going to operate in the world? Which country? You'll be North American based, Asia, Europe. All those areas have different standards in terms of telecommunication, and this way you're not going to receive the same type of signal out of band of your GNSS system. And you also have to start to think about which range can you tolerate between your system and the interfering signal, because you will never be 100% bulletproof, and the concept of trade-off will come. You have to let you know, like, can I accept being 100 meters of the tower and this will work, and not being working at 20 meters of the tower? This is a question you have to ask yourself when you're going to design your system. So what is inside a GNSS antenna? The GNSS antenna is composed of two main components, a passive radiating element and a low noise amplifier, which is active. The passive radiating element is characterized by gain and radiation patterns, where the low noise amplifier is characterized by the gain, noise figure, and saturation characteristics. And both those components will play a role in the interference handling. What is the role of the GNSS antenna? The role of the GNSS antenna is, in fact, that the radiating element and the LNA will work as a team in order to maximize what we call the G over T, which is the gain of the radiating element over the noise temperature of the receiver. This will translate as something like people know better as the carrier to noise ratio. So to do that, the GNSS antenna will amplify the GNSS signal and limit the in-band noise by controlling what we call the noise figure. Another key role is to protect the receiver from the out-of-band interference and transmit a clean signal, clean GNSS information to the receiver. So for that, we're going to attenuate the out-of-band interfering signal by what we call the filtering. If we can't do that because perhaps the signal are in-band, we need to prevent saturation and loss of linearity of the LNA and the receiver. Let's look at the radiating elements. What does it do? The radiating element receives and amplifies the electromagnetic wave, and this depends on two things. It depends on the frequency and the angle of arrival. We have here a radiation pattern showing the gain of a Verostar antenna at the frequency L1. You can see that at zenith, usually the gain is higher than at horizon. So this will have an impact on the GNSS signal, but also on the interfering signal. It will be amplified depending on the frequency and depending on the angle of arrival. Knowing this, you can start to think about some strategy to attenuate interfering signal. This is an example of an anti-jamming antenna we have developed a couple of years ago, where we decided to attenuate the gain of the antenna at low elevation angle. The idea is like most of the interfering signal are coming from the ground level, so low elevation angle. So we took a patch antenna and worked on it in order to attenuate the gain. If you see on these radiation patterns where I'm comparing the standard gain of the patch antenna to the anti-jamming antenna, you can see that at low elevation angle, around like 10 degrees of elevation, we have an attenuation of the gain of about like 20 to 25 dB. So this antenna was measured on a building in the field for over 8 days and compared to a standard timing antenna. And the standard timing antenna was losing the signal for about like an hour and a half over the 8 days, where the anti-jamming antenna lost the signal for only 41 seconds. So that was a huge improvement into the GNSS performance. We are working today on a multi-band version of this because the first product was only an L1 G1 antenna, and the new product should be released next year. What is the role of the LNA? The role of the LNA is to amplify the in-band signal and to filter the out-of-band signal. On this graph, we see a perfect LNA with perfect filtering where you have like infinite rejection level out-of-band, like you have sharp corners on the passband edges and positive gain in-band. But in the real world, things don't work like that. If I looked at a real shape of filter in the, for example, an analog filter, you can see that you will never have infinite rejection levels and you will never have like sharp rejections at corner edges. This can be a problem if you have very close interferences like iridium, let's say, close to the GLONASS or GPS signals, or perhaps in the future with Ligado coming just below the upper band of the GNSS. The strategy could be to use digital filters, but usually if you use digital filters at the antenna level, you risk to have a saturation of the AGC, the automatic gain control. So how can you handle that? One thing you have to keep in mind is like RF amplifiers will generate harmonics and intermodulation. This means that one or multiple out-of-band signal can impact the in-band GNSS spectrum. We had an experience with a customer who was using an antenna and he was receiving a signal from the UMTS 900 megs and UMTS 2100 megahertz. And those two, after going into the first stage of amplification, were generating a spike at 1200 megahertz just in the lower GNSS band, close to the L2 signal. So obviously the degradation was strong. So he worked with us, and after finding the cause of the issue he had, we proposed and designed a filter with him in order to mitigate those signals. So now that we had a filter placed at the front of the first stage of amplification, those two signals were completely attenuated before reaching the amplification, and there was no intermodulation happening in the lower band GNSS. So this solved the problem. But this comes at a cost, because everything here will come at a cost, and everything is about trade-off. Typically, the pre-filter will increase the noise figure of your LNA, which brings a lower carrier-to-noise ratio. And the reason for that is if we talk about filters and the way filters are in the analog world. Typically, if you want a filter with strong rejection and sharp corners at the edges, you will increase the insertion loss. If we look at this graph and compare filter 1 and filter 3, we can see that filter 3 has better rejection, and this rejection comes faster as you go away from the in-band GNSS frequencies. But the insertion loss are higher than filter 3. And the noise figure of your LNA is defined by the front-end components of its structure. So if you have strong losses or insertion loss directly on the input of your LNA, this is the way the noise figure will be set, and then you can't correct for that. So what can you do to protect your system, but still keeping a good noise figure? The idea is to select different type of filters. The idea is to use perhaps a filter with less rejection at the front end, but low insertion loss. This way you're going to set your noise figure before you reach the first stage of amplification. Once this is done, you can add different type of filter which will improve the rejection of the out of band. But you will see, this will also come at a cost because everything comes at a cost in this game. So we're talking about cascading filters. And you can see on this graph on the left, if I cascade filters, I improve my rejection levels, which this is typically what we want to mitigate interferences. But now if I look at what happens in band, we can see that we can suffer from like gain flatness degradation or even group delay degradation. For some application, and especially precision application, you need the gain in band to be as flat as you can, and also the group delay to be as flat as you can. So here we see that we have to do the minimum to get the best rejection, but not to do too much if we want to keep all the characteristics as good as they can be. The saturation point and linearity are also very important. So typically, if an interference comes in band, it will be amplified by the LNA, and you could saturate your LNA and also generate harmonics. So the idea to prevent that is to, at the design stage of the LNA, to get a higher P1 dB or IP3, and this could overcome that problem. This will come at the cost that you're usually going to have a higher current consumption. But one important question first, when you're going to select your antenna, is to ask yourself, what type of gain level do I need? If your antenna is collocated with the receiver, you won't have a long cable between them. And today's receiver will have a sensitivity that they don't need a lot of gain on the inputs, typically around 20 dB or sometimes less. The receiver will be happy with that. So there's no need placing an antenna with a 37 or 40 dB LNA gain just on the receiver input, because this way you're going to amplify more the interference and you're going to have more chance to saturate the system. So the key question here is, how much gain do I need? I talked a few times about trade-off, and this is a slide here to kind of summarize this. Depending on the application, you're going to use different type of antenna, which will come on different type of size. And this has an importance because if you have more like real estate available on your board, you can use different type of filter technologies. For example, ceramic filters will have better insertion loss, but they will be bigger. So you can't usually use those filters if you're using a very compact dual feed patch antenna. You will use more like SAW filters, but those ones will have a higher insertion loss. So for your noise trigger, it could be a problem. Also, all those filters are not reacting the same versus temperature. Like as the temperature is varying, you can have the filter characteristic changing, and this can be a problem if you have a very sharp filters. We talked about the sharpness and the group delay and the flatness, and we talked about the linearity versus current consumption. Also, if you have a system which is very close to the antenna, this is also a trade-off you're going to have to do at one point. What mitigation level do you authorize versus proximity? As a conclusion, I would say that the choice of your GNSS antenna is critical. Some trade-off will have to be done depending on the application and the environment. We will definitely want to go with an antenna which has a pre-filter in order to avoid harmonics and intermodulation. The temperature compensated filter are key if you are using sharp filters with strong rejection levels. One key question also is, how much gain do I need in order to prevent the saturation, which could be also set with P1 dB and IP3 of your LNA at the cost of the current consumption. And for some application, you can shape the radiation patterns. So now I'm going to hand the presentation to Wim, which will talk to you about the receiver aspect.
Thanks, Julien. So my presentation will be about the interference inside the GNSS bands. And I will both address the pathology and the cure to stay in 2020's terminology. We at Septentrio are producing reliable, high-precision GNSS receivers in many flavors, and they're based on our own chips. These receivers, they're used in a large variety of professional applications on the land, on the sea, and in the air. These applications, they strongly depend on the availability of this precise position. And outages due to interference, they could quickly lead to financial losses, often in the thousands of dollars. So before getting to the interference, let's first have a closer look at the desired signal. The GNSS signals are organized in two frequency ranges, one at around 1.6 gigahertz and the other one at around 1.2 gigahertz. And within these ranges, there are many subbands, like L5, L2, and so on. And these are a bit similar to FM radio channels. So each of these subbands is containing some transmissions of positioning signals and sometimes also augmentation signals from one or more constellations. The higher frequency range that's used in pretty much any GNSS receiver. So the one in your phone, the one in your car, and importantly by airliners. Today airliners use this L1 frequency, this frequency band all the time for their navigation. And so there is obviously a safety concern. And for this, it's very important there is no interference in this band, and therefore the ITU and FCC and so on have allocated a dedicated spectrum to this. So only GPS is supposed to operate in this band. At a lower frequency range, we have a different story. So this range, it's used by high precision receivers as they need two frequencies, which need to be a few hundred megahertz apart to come to a reliable, precise position. But unfortunately, many other radio systems are allowed to operate in this range. They're often using high-power terrestrial transmitters, and obviously this will cause interference. In the lower part, so that's the L5 part, that's actually also an aviation band, but it's used by a number of other aviation systems with terrestrial transmitters. Then if we move up a bit, we're at the GPS L2 range, and here in some parts of the world, it's shared with radiolocation systems. So often in a maritime contest, so at harbors and things like that. Then if we move up again, then in the GLONASS L2, BeiDou B3 and Galileo E6 range, there are other radiolocation systems and also air surveillance radar. And importantly, this range is also used by amateur radio. They call it a 23 centimeter band. So yeah, the conclusion is in this lower range, well, there's a lot of potential for interference. So let's discuss the radio amateurs. Radio amateurs, that's people who are fascinated by wireless propagation. And they're setting up video and voice links between each other. So the graph on this slide shows a typical spectrum from an amateur video transmission. So you see a signal which is a few megahertz wide. I think this one, it's an analog transmission. And it's right next and actually slightly overlapping with the GLONASS L2 range. So that will cause interference. Radio amateurs, they have a secondary allocation. That means that they're only supposed to transmit if they don't cause any harm to other services like GPS. But how is this guy supposed to know there is a GPS-guided excavator at a nearby construction yard? That's very hard. So let's now look what kind of impact this could have. So first of all, this interference could cause issues with the precise positioning. So instead of a centimeter level positioning, the receiver only reaches a position which is meters accurate. And this could lead to rather unpleasant situations. If we now look one step deeper and we look at a signal quality in this case, still keeping this radio amateur example in mind, then we see that the carrier to noise ratio of the L2 signal will drop. So in this graph you see the L1 signal, and then next to it the other bars, the blue bars, are the L2 GLONASS signals. They're supposed to be pretty much equal, but in case of this interference you see that the L2 comes down, and for some satellites it's even absent. So the carrier to noise obviously decreases because the noise increases. The interference contributes to noise. So these are indications for an interference, but they could also be indications for something else. And it's often quite hard to see just based on these parameters that there is an interference problem. So we need something better to diagnose the interference. To address this issue, our Septentrio receivers have a built-in spectrum analyzer. So this analyzer, it's available in the graphical user interface, also in the web interface of the receiver. And in a normal situation, the spectrum of a demodulator, which is actually represented into these spectrum graphs, is rather flat because it's dominated by amplified thermal noise from the antenna LNA. Now, in this case, the radio amateur will create this mountain. So you see at the 1250 range, there is this huge peak. That's interference, and that's a clear indication there is interference. Of course, it's a bit hard for a user to start sweeping through all these bands and checking them, and therefore our receiver does this automatically. It will provide a user notification, just a message on its binary interface, which indicates that interference is detected in this case. Interference is detected. It also provides clues about the interference, like its center frequency and its bandwidth. And so this could then be a clue, like we see these frequencies, this is in the radio amateur range, the bandwidth is also something corresponding to radio amateur. So yeah, probably that is a radio amateur. And so in this way, it provides a hint. Now, as this interference in our radio amateur example is immediately adjacent to the GLONASS L2 signal, you can wonder, well, is it not possible to simply filter it out? So this graph is showing, the blue curve is showing the response of the combined GLONASS L2 filter of our receiver measurement. And it is designed to optimally use the GLONASS L2 signal. So you need some bandwidth, but then it also provides a very steep out-of-band rejection. Just at a few percent higher frequency, it's already more than 60 dB down. But still, even though it's a sharp filter, it provides little rejection at this radio amateur frequency. Fortunately, we have a trick. We can manipulate this response of our filters. It's called adaptive notch filtering. So our filters can be manipulated to provide a very high and steep rejection in a selected frequency region of just a few megahertz, or yeah, it depends, it's adjustable. For the radio amateur, it will be, in this example, about 3 megahertz, and then it will just trap this radio amateur signal. So it will be gone, rejected just by this frequency range rejection of this receiver. So this technique is very effective if the interference has a limited overlap with the GNSS signal of interest. As Peter said, so we're not going to throw away the kit with the bathwater. So this rejection of our filters is more than 40 dB. And in some cases, for instance, a narrower interference at the main lobe of a GNSS signal, you can get 100 times closer in this way to the source of the interference before you perceive issues. This method, this notch filter, it's tuned automatically and seamlessly. So often the user will not even notice that something happened. So if we now get very close to the house of the radio amateur, we run into another problem. That's dynamic range, saturation, as Julien already brought up. If this radio amateur signal is very loud, then the noise floor will increase and swallow the GNSS signals. So it's all about amplifier saturation. It could, in theory, be further improved by increasing the power dissipation of the receiver, but also here there are constraints which need to be balanced. On this figure, the blue curve shows the maximal antenna exposure our receivers can handle before the noise degrades at the L2 band. And so the short line in this graph represents the highest radio amateur interferences we've seen in the field. So it's clearly above the blue line, so problematic. Fortunately, we are also receiving the L5 signal, and this is a few tens of megahertz from the L2 band. And this demodulator can then provide filtering, analog filtering into the L2 band, and it can handle 1,000 times more power at this radio amateur frequency. because of the spectral separation. So L5 is in fact a backup for L2 if L2 is interfered. And it's also true in the other way around. If there is an aeronautical service which is interfering with L5, well, L2 is the backup. And so this concept, it's called frequency diversity, and it's often used in radio systems which need to be reliable. So one of many reasons why receiving many frequencies offers an advantage towards reliability. Radio amateurs are typically continuous transmissions. Other types of interference are more time variant. So the top graph in this slide shows a field recorded spectrum of a receiver exposed to interference from a radio location system in a major harbor. So at first sight, it looks like the noise floor increased by 25 dB, just blowing away the L2 signal. But if you look a bit more carefully, and actually this plot shows overlays of short-term spectra, we see that the signal is actually rapidly jumping back and forth between two lobes, between this lobe A and lobe B, and that's called frequency hopping. So in theory, it's possible to see the L2 signal if it's in lobe A, so it's not in lobe B. So another example of this time variant interference are chirp signals. So chirp signals, these are sine waves which rapidly run back and forth in the GPS band, wiping out the GPS band in just microseconds. They're transmitted by some radio location systems and also by the illegal jammers Peter brought up. And they don't care about these illegal jammers. They don't care about spectrum and aviation and so on. They often just transmit in the L1 band. So, but also for this, there is a solution. Our receivers, they have a frequency domain adaptive filter. So we call it also our wideband interference mitigation unit. This will look for these nervous sine waves and knock them down before they can do any harm. And it uses advanced digital circuitry based on wavelet transforms and things like that. And it proves to be very effective against frequency hopping and chirp interference. So in the plot in the picture shows it provides about 25 dB of rejection of chirp jammers. You see that the levels at which you will lose the precise RTK fix are 25 dB higher. That means that you can get about 17 times closer to the jammer before it will hurt. And finally, I would like to bring up an often underrated interference source. It's what we call electrosmog. It's caused by just other electronic devices. So any electronic device, cameras, laptops, and things like that, they will always radiate a bit of power. And the FCC mandates this to be below a certain level. However, even at 3 meters from these devices, the allowed level is still 100 times higher than what can be tolerated by the GNSS signals. And this can occur in all the bands. So common suspects are, well, displays, processor systems, as Peter discussed, also HDMI, USB cables, memory cards, your test laptop, it can all be interfering into GPS. So what can we do against this electrosmog? Well, first we have the tools I discussed in the earlier slides. So these adaptive notch filters and frequency domain adaptive filters, they also work to handle these kind of interference sources. Of course, if you can control these sources, if they're part of integration, then a thoughtful shielding could be a good idea. We also do this in our receivers. We always shield the CPU system of the receiver modules to prevent them from jamming their own antenna. And finally, the awareness is still important. So also here, the built-in spectrum analyzer plays a role. It can provide hints to shift some of the system frequencies in the integration. So to conclude my presentation, I think we can say that interference is a major concern in GNSS navigation. Out-of-band interference, it's first handled in the antenna. And as Julien discussed, avoiding intermodulation, so mixing of out-of-band frequencies into the GNSS bands, that's something which should really be avoided at antenna level. And for this, a thoughtful filter distribution is important. So it's important to balance the sensitivity for the robustness of the system. And finally, the in-band interference as well, they're to be handled by the receiver. So I was discussing the modulated continuous interferences like this radio amateur interference. And this can then be handled by this adaptive notch filtering. Frequency hopping, like this radio location system, and chirp, like from jammers, this can be handled by this frequency domain adaptive filter, or WIMU. And then finally, if the interference levels start to get really excessive, or if the interference is simply unmanageable, then frequency diversity offers a way out. And this concludes my presentation, and I now hand over the mic to Mackenzie.
All right, thank you all, that was great. We are now going to jump into our Q&A for the questions that we have received. My first question is for Wim. How resilient are the current GPS, Galileo, BDS open signals to the planned Ligado network?
Mm-hmm. Yes, so as a first remark, it's well important to say that Ligado is close to the L1 band, so it will not affect the L2 and L5 band. So the signals there are in principle safe if the receiver design is done properly. Now, for the L1 band, the most vulnerable signals depend a bit on the receiver design, so like aliasing frequencies and things like that. Now, we did with our receivers quite some tests on that. We are replicating the Ligado interferences OFDM signals with signal generators and add it to the GNSS signal and see when we start getting in trouble. So we could see that at levels of minus 36 dBm, so that's what you would get if you're at about 100 meters from the tower. There starts to be some slight degradation, and this is on, in fact, all these L1 signals together because it works via saturation. So you see it on L1 Beidou, Galileo GPS. Then we only lose a precise position if you get much closer to the receiver, to the antenna. And that's not accounting for any antenna filtering. So I think if antennas with some filtering at the Ligado frequencies, like the ones from Talisman, are applied, then it's quite robust.
Okay.
So yes, that's what I can say.
For a follow-up with that, will GNSS boards provide adequate filtering to overcome these limitations?
Mm-hmm. Yes, so for GNSS boards, there is no standard or something like that for this filtering. There is, of course, an ETSI standard for adjacent band filtering, but the levels specified in there are way too low to cope with this. So it's a matter of receiver design, and we take this into account and make sure the filters are steep enough. And I think in the future that will be more and more of a concern as the spectrum start to be much more packed. It's not just Ligado, but also other countries are, well, except from US, are starting services in or around the same frequency range, so above 1500 megahertz.
Okay. This next question is for Julien. What are the greatest sources of GNSS interference in the US?
Most of the information we have comes from feedback from customers, and I would say that what is most common is usually interaction of Iridium and Inmarsat system very close to GNSS antennas. These are coming back quite often, and that's why we develop filters for these. Also, cell phone towers have been an issue, especially for people using non-pre-filtered antenna. And I say that because, in fact, it can seem to be an easy solution to have a pre-filtered antenna, but there is a lot of antenna on the market today which don't have pre-filtered antennas. And this had a great layer of protection. So cell phone antenna usually are taken care of that with a pre-filter. And obviously, we hear a lot about Ligado, which is non-existent yet, but it's planned. So these are mostly the source of interference we hear the most about. But it will really depend on the system, where you are operating, and things like that.
Okay. This next question is for Peter. Why is Ligado so stubborn to not agree to move their frequencies? How many times do GPS experts have to run tests and prove that Ligado does interfere with the GPS spectrum of frequencies? This audience member believes that this was tested and decided years ago.
Well, hey, I am skeptical that there is any level of mitigation that they could apply that would totally eliminate the problem. As we've said, you can have problems even with LTE. But specifically for Ligado, it's a money thing. You know, some years ago, they paid a significant chunk of money to acquire that band, and they've invested a significant amount of resources since then in lobbying to convince the FCC that they should be permitted to run a terrestrial comms network on that channel. And I believe they even went through bankruptcy. So at this point, their investors are breathing down their necks saying, you know, find us value for this asset that you've got. So I suspect this is just rent-seeking behavior, and it doesn't even matter if it's Ligado or somebody else. If Ligado goes belly up and sells that band to someone else, we're just going to have the same problem again. Realistically, it's just something that we have to deal with as it comes. It does look like from reading some of the FCC filings that they got a pretty sweetheart deal in some ways. And as an amateur radio operator myself, that pisses me off, excuse me. But we believe that there are good techniques available for mitigating many of the problems that will arise, and there are robust communication channels that, if necessary, we can escalate issues to get them resolved. Unfortunately, that's going to have to be done on a case-by-case basis.
Okay. We have time for one more question. So this one is for Wim. Which sources of interference are more severe and need to care?
So the most severe sources of interference are sources which are overlapping with the GNSS bands and permanently there. So if it's not really jumping back and forth, there is not much you can do on a single antenna against these interferences. So then the way out is, of course, frequency diversity. So a typical source like this is this electrosmog from other devices. I've seen cameras which just raise the noise floor by 20 dB at L1. So these are really the worst ones, I would say.
Okay. All right, and that wraps up our questions. Thank you for attending today's webinar, GNSS Interference, Sources, Effects, Detection, and Mitigation Techniques, brought to you by GPS World Magazine and the sponsor of our event, Talisman. If you have any additional questions for myself or for our speakers, you can reach out to us directly via the email addresses you see on this slide. The resources panel houses a PDF of today's presentation slides, which you can download. To access this panel, click the green icon at the far right end of the toolbar at the bottom of your screen. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World will also be posted to this page. Thank you all for attending, and we hope you'll join us for another great webinar.